This is the Commodore C16 that was unboxed alongside its +4 sibling, and neither of them wanted to cooperate. In the last episode, the +4 gave us nothing but a black screen before it finally came back to life, and this one is following the same theme. Mostly a black screen, sometimes a solid colour, but never anything useful. Let's see what this machine is trying and failing to tell us. Welcome back to Erie's 8-Bit Workshop. This is a retro, rapid, fast-paced, real-world retro repair where we follow the evidence and leave the surprises intact. On the bench today is the Commodore C16 that arrived alongside the +4, and right now it's doing its very best impression of a powered-on brick. Most of the time it boots to a black screen, occasionally to a solid colour, but never to a working system. So let's get straight into it. So we have this Commodore C16, and when we switch it on, all we get is a black screen. So again, not particularly helpful. There's no error messages. There's nothing for us to go on. So we're going to start by opening it up and having a little poke around with the scope. First thing we're going to do is just check the voltage and the clock on the CPU and just make sure that we're actually getting some kind of signal through. Okay, so pin 1 is the clock. And that looks good. Pin 5, 1, 2, 3, 4, 5 is 5 volts. So we know we're getting good voltage through on the CPU. We know we're getting a clock. So let's check the address lines and the data lines. So they start from pin 6. So 1, 2, 3, 4, 5, 6. We have something. 1, 2, 3, 4, 5, 6, 7. All looks good so far. 8, 9. That doesn't look good. 8, 9. So pin line 9 looks a bit off. 10 looks off. 11. That's 12. 13. 14. And 15. So there's about half the address bus there seems to be zeroed. How about the address bus? Let's go across that. So we're on 21, 22, 23, 24, 26, 27, 28, 29, 30, 31. That looks okay-ish. 32, 33, 34, 35, 36, 37, 38. Okay, so the data bus looks okay, but we've got a few pins here which are not. So they're from pin number 20 is ground, so 19 is 13, 12, 11, 10, 9, 8. Okay, so 9, 10, 11, 12, 13 and 14. So we've got 5 stuck bits. Now the CPU is the thing that generally drives the address bus, so I think that we probably have a failed CPU here. So let's try swapping this out for the one from the +4, which we know is a known good. Okay. Well, that's changed the picture somewhat. We do now have output on the screen, so I think almost certainly we had a problem with the CPU there, but clearly not the only issue at hand. So let's just check those data pins and address pins again. 1, 2, 3, 4, 5, 6. Okay, so that's A0, A1, A2, A3, A4, A5, A6, A7, A8, A9, 10, 11, 12, 13, 14, and 15. Okay, so the address bus looks okay. Let's try the data bus, which goes from 31, 31, that's D7, D6, D5, D4, D3, D2, D1, and D0. So it looks like the CPU is executing code, and there is stuff on the data bus, but quite clearly from the picture we have garbage being executed. What could that be? Well, I'm drawn to there being an issue either with the ROMs or with the memory. So the ROMs are actually easier to check. What we do is we take these chips out and dump them and compare them to an good image. So that's, I think, where we'll go next. So the first one is the basic ROM. Actually, we can see if it's the basic ROM without dumping it. The system will still fire up with a working OS, but no basic ROM. It just won't go very far and will come up with an error message. So let's just take that out and turn this back on and see whether we get the same corrupt image. So the basic ROM is good and not the cause of the problem. Basic ROM is probably good and not the cause of the problem. Okay. So we can see, given the checksums are the same, that the kernel actually reads out okay from the image. So all good from that perspective. So I'm going to turn my attention onto the memory. Now there's two parts to the memory. Here's the memory ICs here, each of which contributes one nibble or half a byte to the 8 bits. They use a multiplexer, 24LS257, in a way to convert the addresses on the proper address bus to an address which the ICs are going to use. So we're going to need to, we've already scoped this side of the bus, we need to scope this side of the bus. So we're looking at pins 6, 7, 8, 10, 11, 12, 13, 14. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. What was the last one? 14? 13 and 14. So not that one. 13 and 14. Well, that, that actually doesn't look very good. We have some flat lines. 1, 2, 3, 4, 5, 6, 7, 8, yeah, okay. So we've got some flat signals there. Now, they're generated by U7 and U8, which according to the schematic are 74 LS257s, but this one here is a MOS chip, a 7708. I'll be right back. I'm just going to go and check out a schematic for, sorry, a datasheet for a 7708. Well, apparently a 7708 is a 74 LS257. It is actually the same IC, just made by MOS. But the 7708 is actually prone to failure. So I'm going to probe around here on the output pins and see if that is the cause for our no signal. So we want pins 4, 7, 8 and 12. 4, nothing. 5, 6, 7, 8, nothing. 9, 10, 11, 12, a high signal. So I think there's our problem right there. Let me check these same pins on U7. 4, yep. 5, 6, 7, 9, yes. 10, 11, 12, yes. Okay, so this one is showing all the signs of being dead. Oh, and it's actually really hot. So I'm going to desolder this one now, and we'll swap in a known good or a new chip. So it's failed on the IC tester, which isn't a great shock. Let's pop one of these. Oh, test this one before we put it in. '74 LS 157 or 257. So this one's passed, and we'll pop him in there. Okay. Changed the picture, but it's still not working. 2, 3, 4, 5, 6. So 6 now looks okay. 7, 8 is ground. 9, 10, 11, 12, 13, U7, pin 4. It seems okay. One, two, three. Okay. So the addresses all now look fine. So we need to look somewhere else. So after swapping the LS257, the machine still isn't working, but now the address lines to the RAM look correct. That's definite progress, if it hadn't been for the fact that I missed something. Next, I plug in the diagnostic cartridge. This time, it gets as far as the checkerboard screen with a border that flashes black. Reading the diagnostic documentation, honestly, I'm not entirely sure whether this indicates an address line problem or a data line problem. Either way, it's still failing during the low-end memory test. And so, off camera, I start removing chips. First U5, then U6, both memory ICs test perfectly. Still confused, I remove U7, the other multiplexer. That also tests fine as well. Very confusing. Okay, the flashes we have would indicate that we still have a problem with low memory. I've tried taking out and resocketing the memory here on U6 and U7 and they're fine. The other LS74257 is also fine. I've taken that out, tested it and put it back in again. So that leaves me with the possibility that in the desoldering, I've actually damaged a trace. So what we're going to do here is just quickly go around and test the continuity of this LS257 to the remaining circuitry. Okay, and I think I may have found the issue here. Pin 4 is supposed to be connected to the resistor pack here on this second end pin here, and I'm not getting anything, so it's possible that I've broken the trace. So it should be pin 8 on the other side of the resistor pack. 1, 2, 3, 4, 5, 6, 7, 8. So we've got the connection onto pin 8 from here, but the other side of the resistor should connect to pin 4, but doesn't. So it looks to me like we have a broken trace between pin 4 and the second pin on the resistor pack just here. Now the quickest way of testing this is with a jumper wire. If I pop that in pin 4, like that, and then turn on, and there we go. So we're on to the rest of the diags. So I'm going to put a bodge wire between pin 4 and the second pin of this resistor pack just here. With that done, Let's try the diagnostics again. And there we go. The diags are continuing to run after the low mem testing has been completed. Perfect. Okay, it looks like we have a working system. Now it occurs to me, now that we've completed all of this extra hard work, albeit unnecessarily, that it would be very easy to upgrade the system to 64K. All that would be required would be to swap these two ICs out for larger ICs, 4464s. Now I've got a couple of those in stock, and then we need to introduce a couple of address lines that are missing from the LS257s that are currently tied high. So two bodge wires adding A14 and A15 to these chips, and the memory upgrade will be complete. Let's do it. So in order to upgrade this to a 64K machine, all we need to do is swap out these two chips here. The memory are 4464 chips, which are pin compatible with the 81416 4416s. We just need to supply it with a couple of extra address lines. Now, these two multiplexers deal with the address lines, and two of their pins are currently tied to high, meaning that they can't address the full memory map. So if we provide it with A15 on U7 pin 2 and A14 on U8 pin 14, then we can address the entire memory map. Now they're currently tied high, as I say, so we're going to have to cut the trace first. So if I look down inside the socket here, I can just see that there is a trace going between pin 2 and the 5-volt supply on the last pin. So let's cut that one now. And we have no connectivity. Great, that's been done. And we'll pop the IC back in again. And then flip the board over, and then just by pin 7, we can just cut the trace there. We have no contact, and that's the trace done. So now we just need to provide it with the A14 and A15. Now, just to the right of the CPU, there's a small group of 3 wires, and 2 of those are A14 and A15, so we can take them directly across from those. Those would be the easiest ones to get to. A14 and A15 not provided to the kernel, but they are on the TED and the CPU. But if we can get away with not soldering directly onto the CPU or the TED chips, that's probably a good thing. Just add a bit more solder here to give it something to grip onto. So this one is A14, and A14 is going to go along to pin 14 of U8. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, and I have no short for 5 volts, so that's good. And this goes on to pin 2, just there. And there we go. And that should be that. So let's pop the die cartridge back in again, and we'll have it check the memory. Perfect, it says 64K just there. Okay, so easy fix and quite a straightforward upgrade as well. So we've replaced the CPU was faulty. We've replaced the LS74 257 memory multiplexer. The MOS version was broken. Got led down a bit of a rabbit hole here, which caused me to socket the memory and the other multiplexer. But it turned out to be a broken trace between the resistor pack and the multiplexer that we swapped originally. So obviously I damaged something in the process. Now this particular process, the wires seem to be particularly fragile and actually come out with the ICs, and that one did, unfortunately. Then we upgraded it with 64K of memory. So now we're capable of running any of the +4 software as well, as long as it doesn't use the user port, obviously. Let's get this thing back in its case. But before we do, let's pop the service stick in, just to remind myself what was done and when. We're also going to add a couple of heat sinks to the TED chip. These things get nice and toasty, and this hopefully will extend its life. Okay, get the top back on and the plugs back in. And we can test out the keys. It's still seeing the 64K, which is good. And let's quickly run through every key and just make sure we've got them all working. And it all seems to work. Fantastic. Okay, let's try out some software. I've got 2 tapes here which came with the +4. Now, they normally would have C16 +4 if it's compatible with the C16, but since we've done the upgrade, we should be able to run either of these, Icicle Works and Treasure Island. Now, we tried Icicle Works last time, if I remember correctly, on the +4. It's a Boulder Dash kind of game. I'm not sure about Treasure Island as yet. I've never tried it. Okay, let's get this thing loaded. And we'll obviously speed up the loading sequence. And it's running. Brilliant. And off we go. Let's see if I can complete the first level this time. Each 20 seconds to go. Ten. I'm not gonna make it. Come on, come on, come on. Out of time. Alright, let's try Treasure Island. And hit 2 loads. That's fantastic. So our upgrade is definitely working. I can't seem to find any keys for this one. Quick look at documentation. Well, that's a shame. We're not going to be able to play Treasure Island. It appears that it needs a joystick, and I don't have one. But we can see that it is running, so that's great. It's fantastic. So this Commodore C16 went from a black screen and floating address lines through a dead CPU, a failed MOS multiplexer, a broken PCB trace, and finally into a fully working and upgraded 64K system. It now runs +4 software, passes full diagnostics, and should be far more reliable than when it left the factory. And if you've enjoyed this repair, please do give the video a like. It really helps the channel. And if you want some more real-world diagnostics, repairs and upgrades, make sure that you're subscribed to Erie's 8-Bit Workshop. So thank you very much for watching this episode, and I'll see you in the next Retro Rapid. Goodbye.